Hello everyone, my name is Riccardo Zanon from ArcelorMittal Global R&D, and together with my colleagues and co-authors, I would like to present you our proposal for a simplified analytical method to assess the sagging bending moment resistance of shallow floor beams, also known as SFB, under standard fire exposure. In the first part, I will present you the motivation for this work, then we will discuss the application range, and then more in detail the simplified method which is proposed, and how it has been validated based on experimental data and the comparison between the numerical and the analytical results. And then we will finally come to the conclusion. Shallow floor beams are an appreciated solution for residential building as well as for office buildings, thanks to the fact that the depth of the beam is integrating into the floor 8 itself. I will not go into detail, I will just show a picture from a recent example which was built in Luxembourg, and you can see that there is a double T asymmetric section which is supporting a composite slab which is posed on the bottom flange of the steel section, and there is a reinforced concrete which is poured on top of the steel decking as well as of the composite beam. The beam is made composite by use of shear connectors. As you can see, there are important longitudinal reinforcement which is parallel to the beam itself and which serves as a reinforcement in the case of fire. In this case, there was no need of fire protection even for a very high fire requirement of 120 minutes. This is the finished floor system with the integration of the installations and without any fire protection. In the frame of our work, we have defined a very specific application range. I will not go into detail, it is reported on the slide as well as on the paper. I just want to recall that we have selected for this part of the study a double T section formed by a rolled section with or equivalent and a plate welded on the bottom part. The plate is wider than the bottom flange of the beam, so to serve as a support for the floor system, which is typically a prefabricated system either of concrete or from steel. This cross-section is also known as SFB or slim floor beam. Now I will briefly present the model which has been proposed. We consider a cross-section which is heated from below and it is not heated from above, so the thermal gradient is coming from downside. And we will analyze the different elements which contribute to the resistance of the beam. The first one, coming from the top, is the concrete flange. In this method, we propose to consider only the part which is staying above the upper flange, and we will consider it as unaffected since the minimal concrete cover which are specified in the application range are enough in order not to have temperature too elevated so that it is needed to consider a reduction factor. The second element that we consider is the top flange, which is also considered as unaffected as long as the concrete cover specified in the application range are satisfied. The third element is the steel web, which is considerably affected by the fire exposure, and therefore the temperature has to be calculated. We propose to use the formula initially proposed by Zaria and Franzen, but we consider just a uniform temperature along the wall 8 of the web. This is a simplification, but we consider it as more relevant for the practice since it is easier to calculate the sagging bending resistance, and in terms of precision it was enough, as it will be shown after. For the longitudinal reinforcement, we also propose to use a formula which is based on the literature, whereas we fix the distance with the concrete cover in order to simplify the procedure for the practitioner. For the bottom flange, we propose to use also a formula which is present in the technical literature. The same approach is also used for the bottom plate, with the specificity that the width of the plate has to be reduced for the calculation of the sacking bending moment in longitudinal direction during fire, due to the fact that the tip of the flange has a more severe fire exposure than the central part. The formula is given on the slide. The model that we have proposed is based on technical literature, but we wanted to validate it also on our side based on a FEM model. The FEM model was validated based on 3 tests that we consider as representative for the cross-section that we wanted to cover. Once it's with a full concrete slab. The second is with prefabricated elements. And the third test is made with a steel composite decking, which is posed on the bottom plate of the steel cross-section. I will not go into details into these charts, but it is just to show that for each of the tests, a quite detailed analysis concerning the thermal model was performed in order to show that the analytical method delivers results which are compatible with the experimental results, and that the numerical FEM simulation can also replicate the temperature which evolves in the cross-sections quite properly. Beside the thermal model, of course, there was also a mechanical model that was launched. All the simulations were done with the software Saphir by University of Liège. And here you can see the main results, namely the mid-span deflection for the 3 tests that I've showed before. In all 3 cases, the ultimate bending resistance estimation is quite close with the one of the tests. I would say also the load displacement behavior is reasonably close for the 2 first tests, whereas for the third one with the composite decking it is a bit different, but I would say it's still reasonable for a fire test. With this numerical model, a parametrical analysis was performed with more than 1,200 simulations covering the application range that was discovered before. The results are shown on this graph, which show on the x-axis the bending moment resistance calculated with the analytical model, and on the y-axis the bending moment resistance calculated with FEM model. In general, it can be seen that the results are on the safe side, since they are all in a range of plus 10%, minus 35%. That means that the analytical model delivers results which are maximum plus 10% than the FEM model, or minimum minus 35% than the FEM model. This was done for R30, R60, R90, and R120. On this chart, we show the results separately for the 4 different classes. As you can see, the spread is increasing by increasing the fire exposure, as it can be seen, but the method was set in order to be quite safe-sided. That means that also for R120, the results are reasonably safe. You can see also the mean value and the standard deviation on the bottom part. So for each of the resistance class, 300 simulations were performed. On this chart, we show a probabilistic assessment of the method with on the x-axis there is the ratio between the design value, so the value calculated by the analytical method, and the reference value, which is the value calculated by the numerical simulations, so by the FEM model which was validated before. And the number of cases which has been attributed for each family. As you can see, the method is significantly safe-sided, as the average lies at about 0.85. There is for sure a certain deviation, but in our view it is acceptable for a farm method, in particular because the number of cases which increase, which have values above 1.0 are really minimal. So now we come to the conclusion. And briefly said, we think that the method that has been proposed in this contribution is significantly safe-sided, and also is relevant for practitioners, since it permits to calculate the second bending moment resistance in a quite easy and therefore quick way, avoiding numerical simulations. This can of course be just a simplified method that in case of need can be substituted or improved by advanced methods, but it offers a very simple tool for practitioners to assess the fire resistance for isofire ratings. Thank you very much for your attention, and I remain at your disposal for any questions. Thank you.